Okay, so this is more of those same type of problems of what we did. The many problems, the exponential, these are called exponential growth and decay. I told you guys on Friday when we did them, these next to linear problems, and actually probably even more so than linear problems, except they're a little harder, so we don't teach them to you in the 9th grade. You will use these whether you take any math past high school or not. Because this is how money, when you borrow money, this is how your interest accumulates. When you invest money, this is how interest accumulates. It is also how things depreciate. If you ever owned your own business and purchased business equipment, we do one in a minute, that's a tractor if you own a farm, you have to depreciate your items when you do your taxes. So it is something that affects everybody, these particular formulas. Now you don't usually do them by hand. There are all sorts of programs and things that will do them for you, but somebody writes the programs. If you think you might be going into finance of any kind, you won't have to take calculus in school. You'll take finance classes, but these are finance related. So you will deal with these kind of problems later on, because that's what you do when you do finance. Okay, so in the top left corner, if you look, here's your formula. This is both the exponential growth formula and the decay formula. They've put it all together into one formula, which is why it has that funky symbol inside, the plus minus. If it's 1 plus r, that would be growth. And if it is 1 minus r, that would be decay. They just put it all there together to make it easy to see and easy to find. A sub O, which sometimes people call A naught. A sub O is the original amount. We already talked about that the other day. The A value is your original amount. Easy to find on the table. It is always right there with 0. So it's real easy to find. R is the annual percentage rate of increase or the percentage rate of decrease. T is time in years. And then Y of T is the amount after 2 years. Now, for right now, the first couple of problems, we're doing annual rates and T in years. When we do these as they relate to science, these are the same things you use to determine population growth. Sometimes our time switches to days or even minutes, because things like bacteria and viruses, they both grow and decay in seconds time. So our time value will switch. But for right now, we're talking money. So all of these on the front are going to be annual percentage rates and time in years, because we're talking about items that you use money, either investments or loans. Okay, so right now the population of our town is around 25,000. However, the number of citizens is projected to increase about 8% every year. What will the population be in 4 years? Now, we could just plug the numbers into the formula and get what it will be in 4 years, but they put the table. So they don't just want what it is in 4 years, they want to know what it is each year after the first one. So remember, your A sub O, or your A value, is the original amount, which is 25,000. And it always goes in the front. The formula at the top of the page tells me that I'm going to do 1 plus R or 1 minus R, depending on whether or not this is growth or decay. So in this case, am I doing 1 plus R or 1 minus R? 1 plus R. So I'm going to do 1 plus 0.08. So my formula is going to be 1.08. So I'm going to go ahead and plug that into my calculator. And then go to my table. So in the 4th year, my population is 34,012. Is everybody okay? Anybody need any help plugging it into your calculator? Everybody got it? Alright, so that's a growth problem. Problem number 2 Mr. McDonald bought a farm tractor for $60,000. For his tax purposes, its value is expected to depreciate at a rate of 18% annually. What will the tractor's value be in 4 years? Your A value is always your initial value, so $60,000. Not only does it go in the front of your formula, but it will also always be the y-intercept, so you can put it right there with your 0. Now, is this a growth or decay problem?
Okay.
Decay, so I have to do 1 minus 18%, which means this is going to be now, I went ahead and wrote it out, 0.82, but in your calculator, you could just do 1 minus I could just plug it in like that, 1 minus 0.18. What happened to my table? Yeah, what was wrong with my table? I know it wasn't appreciating that much. So in the 4th year, my tractor is worth $27,127. Everybody okay? Okay, so on problem 3, we got a plant sending 50,000 cubic feet of CO2 into the atmosphere annually. They've signed an environmental agreement to cut their emissions by 12%. To what level will the carbon emissions drop in 4 years? Your AO, or your initial value, is 50,000. Now, is this growth or decay?
Good.
So you do 1 minus is what goes in here. So far, so good? Alright, problem number 4. College fund. Jenny's parents invest $5,000. That's your initial investment 4 years ago. The account has now reached $6,312. What is the approximate annual return rate? Okay, so we talked about on Are You Able with a table that your A value is so easy to find. It's always right there with 0. So that's this value. How did we find that B value again? Subtract. Divide. So always divide the second number by the first. So I'm going to do, in my calculator, I'm just going to do 5,300 divided by 5,000. Second number divided by the first. And I get 1.06. So that's what's going to go right here. The only thing is you got to be careful about what the question actually asks is, what is the annual return rate? Or what is your rate?
6%.
6%. Because remember, the formula has the 1 in it. So the 1 comes from this formula. It's the 0.06 that is the return rate. So when I find my 1.06, 6% is my return rate. Is everybody okay? Alright, now when we flip the page, these are all going to be, this whole page is all banking. This is all investment. I am investing and I am earning interest. So they are all growth problems. Now if you look at the very one at the top corner, it's the same formula as on the other page. It's just they took the minus off because we're just growing. We're not doing any decay problems on this page. So it says a general formula can be used to describe quantities that increase at a certain percentage rate. In finance, we call it interest. However, when banks handle investments or loans, they do not simply apply your interest once a year. Instead, they give you a little bit of interest throughout the year. So instead of, let's say you put $500 in the bank on January 1st, 2016. They are not going to wait until January 1st of 2017 and give you your interest then. They are going to give you your interest at some interval along the way. So the formula has to change slightly. If you'll look over here on the left-hand side, it's essentially the same formula. AO being the original amount, 1 plus R divided by N. That N represents the number of times in a year that they're going to pay you interest. They might do it quarterly, they might do it monthly, they could do it weekly, they could even do it semi-annually, which would be twice a year. So that's what the N represents, is how many times they actually give me interest. It's called compounding. So whenever you go to borrow money too, but whenever you go to put money into a savings account, one of the things you want to know, and that they will tell you, is how often they compound interest. That means how often do they pay you your interest. So let's look at what it does. On the first one, they filled in the first one annually. That's once a year they pay you your interest, and they filled in that one. We're going to do this first example on A. They're going to compound quarterly. So how many times a year are they going to pay me? 4 times a year. So my N value is going to be 4. So my initial amount is $6,000, invested at 4%, so that's going to be 0.04, divided by 4, because it's divided by N, raised to the 4t. So if you look, the formula again is over here. Your initial amount, 1 plus the rate, you do have to move your decimal, divided by the number of times that they pay you, and then this is the same N value down on the bottom as up and top. So I'm going to plug that in my calculator. The initial amount is 6,000. 1 plus, I'm going to go ahead and use the fraction bar, 0.04, because it's 4%, 4 times a year, raised to the 4x power. Now, your table, it cuts off because the table is only so wide, so I can't see all the decimal places, but I don't know if you knew this, but if you go over and highlight it, the actual decimal places are down here at the bottom. Which, because this is money, I need them. I need 2 decimal places. So it's 62 cents. Everybody okay? Now notice in year 5, I made more money even though my initial investment was still $6,000 and my interest rate was still 4%. I made more money if I compounded quarterly. Why is that?
Because you're saving up your money to give it a different time, like.
Yeah. Because when they pay you interest, it goes into your account. So instead of earning interest on $6,000, you're now earning interest on $6,000 and some more money that they have put in there for you. So the more often they can compound, the better off you are, because that means your balance is going up as they calculate interest. All right, so let's see what happens if we do it monthly. So my end value is 12. It is still initial investment of $6,000. It is still at 4%.
How do you plug it in?
How do I plug it in? 6,000 is my initial investment. 1 plus, and then I use the fraction bar, 0.04 over 12, and then raised to the 12x power. Now on C, it's the same problem. So we're still starting with an initial investment of $6,000. We're still 4% interest, but this time they want their interest to be given to us compounded weekly. So what is my end value if they give me interest every week?
52.
52. So it's still $6,000. Interest rate is 0.04, but this time it's divided by 52. Now this time it's 52 times 5. All they want us to do is find what it is in the 5th year. But because this is already in my calculator, I'm just going to go in and change what was 12 to 52, and I'll just look at 5 on the table. Since this is already in here. So I got $7,327.85. And then the last one of these, same, everything else is the same. Initial value, 6,000, rate 4%. This time they want to compound our interest daily. How often would that be? 365. This year it's 366. But they won't, they won't use 366. If they were doing this, they would still use 365. So since it's in my calculator, I'm just going to go change what was 52 to now 365. So, if they compounded annually, that gave me this amount right here, $7,299.92. If they compound daily, I get $7,328.34. So what is a better deal to you?
Daily.
If they compound daily, you get more money that way. All right. Those were all growth problems. Now we're going to look at a couple of decay problems. They've given us a function. I know already before I even plug this in my calculator that this value right here is going to be 500. Because it's your A value. It's always right there, right in the front. Okay, radioactive material loses mass over time because some of its nuclear material is released as radiation. The mass of a certain sample changes according to the equation on the left. After approximately how many years does the sample have only half of its original value? So I'm going to plug this in my calculator, just like it's written. After how many years does this sample have approximately half of its original mass?
4.
After 4 years. This is called the material's half-life. So, next question. Will the substance be gone after 2 half-lives?
No,
No. Why not?
because it'll never really be gone if it just keeps on dividing into.
Exactly. And if you look at it, let's look. There's 4 years, so it's at 250. 2 half-lives would be 8 years. That's 125. Well, 125 is half of 250, not half of the original substance anymore. It keeps halving what you have. Halving what you have. So, it will never be gone. You can have something and have something and have something and it will never completely go away. And yet, if you wanted to, you could scroll this table and just keep scrolling and see that it doesn't matter how far I go, it is never completely gone. So right now I'm at 60, 70 years and there's still something there. And there always will be, because it's never going to be completely gone. Okay, next one. This is a different radioactive substance. It loses half of its mass over a 6-year period, or its half-life is 6 years. So I have a 1,200 gram sample, and it's going to decay into a 600 gram sample after 6 years. They want us to determine the rate at which it decays. So on your A with a table, we knew easy A. The A value is always with 0. So I know that front value that's easy. How am I going to find the value that goes inside the parentheses?
Well, it's like the first.
Divide the second by the first. So I put in my calculator 1069.1 divided by 1,200.
189.
I get 0.89. So that's what goes right here in the parentheses. Now, here's where you have to, again, be careful about what they ask you. Determine the rate at which the substance decays. 0.89 is not the rate at which it decays, it is what remains. If you remember from the formula, remember your formula is AO. This is a decay problem, so it's going to be 1 minus the rate raised to the T power. Well, I now know this inside piece. 1 minus R equals 0.89. So now you can solve and figure out what your rate is. And your rate comes out to be 0.109, or you could say 10.9%. That is the rate at which it decays. All right, now that I have a formula, I'm going to go ahead and put it in my calculator. Because the next question asks me to find Y12. So if you put it in your calculator, you can just go straight to the table. So I put in 1,200, 0.89 raised to the x power. There's 12, which is 296.39. Do those values make sense? Yeah, because it's approximately half. Because if this is almost 300, and half of 300 would be 150, that's almost 150. So yeah, from 12 to 18, that's 6. Every 6, it should half again. So if this is approximately 150, in 6 years, it should be around 75. All right, now it asks us a question, for what interval of time will the amount of the substance be greater than 400 grams? So I'm going to go ahead and just hit graph and see if I can see this in my calculator. Now, I just hit graph, and it's in a standard window. I cannot see it. Now, I'm not completely surprised, because if you look at your table, look at what your Y values are. They're huge. And my standard window just goes up to 10. So I need to adjust my window. So let's hit window. Now, in this case, in this problem, what do your X values represent? Years. So do you need any negative?
No.
Okay, so I'm going to go 0. Probably 10 might be fine, but let's go a little higher. Let's go 20 just because. Since I don't have any negatives, I'll just go 20. I'm going to count my 2's. Okay, now my Y minimum, we already talked about this. Is the substance ever going to be completely gone? So you don't need any negatives. Let's just go to 0. Your Y max starts at 1200. Since I want to see the 1200, I'm going to go 1300 just so I can see the top of it. And let's go ahead and scale it by hundreds. So if I hit graph, it should, there it is, should show up. Alright, so now I need to know, because the question asks me, when will the amount of the substance be greater than 400 grams? Well, how am I going to know where 400 grams is on this graph? Do what?
Second.
You could trace. I could do that. I could just do this and see if I can get to 400. Or what would be easier?
Your graph, or tray table.
If you go to your graph, put in 400. What is that going to draw?
On a straight line.
Straight line. Now I know where 400 is. It's going to be at that intersection. So I'm going to do second trace and intersect. It is at 400. It's at exactly 400 at 9.427. It asked me where it was greater than 400. So what it's really asking me for is this entire interval. From here to here. Now remember, when they ask you for intervals, they want X values. What is the X value right here?
0.
So I go from 0 to 9.427. Not included because it didn't ask me where it was greater than or equal to 400. It asked where it was just greater than. Is everybody okay? Now, if you look at the top, they just did all what we just did. That's what this is. That's what we just did. So right now, I want you to do problem number 8, 9, and 10. They are just like what we just did. So you're going to plug them in your calculator and see if you can find the interval. Yes. Okay, so I went ahead and put in the left side in y1, 500, and then 0.4 to the x power, and the right side in y2. And then I went to window, and I set my window exactly like they have theirs set. From 0 to 5, counting by ones, and from 0 to 500, counting by 100s. So when I did that, my graph came out to look like this. And the question is asking me, where is the curve? You read the way the question's worded. This is the exponential, or the curved piece. Where is the curved piece less than or equal to 32? So if I look at my drawing, I'm looking from here, that piece of graph. Because I'm looking for where it is less than or equal to 32. So I need to do an intersect. Can't even see it. I got x equals 3.
That's one
Remember, it's x values that they're looking for. So I got x equals 3. And if you look at your picture, it's from 3 to infinity. So your actual answer is 3 included, because it said it gets to equal 32. It's less than or equal to 32. So 3 to infinity.
What did you enter as your Y1?
As my what? As my which thing?
Your Y1.
My this.
Oh, shoot.
Did it backwards.
No, I just put .04 instead of .4.
All right. So same thing on number 9. Go ahead and put number 9 in your calculator. Okay, before I even put anything on here, what is different about this graph?
It's scrolling.
It's growing. This is a growth problem. So it looks like this. My question asks me, where is the curve greater than 50? So you were looking for this piece of graph, where it's greater than 50. So you're still going to have to do an intersect. I got 7.94. And it's from there to infinity. So I'm going to put 7.94 to infinity. The 7.94 is not included this time because of the way the... No, it is. I'm sorry. It's greater than or equal to. So it is included. Because it is a greater than or equal to sign. Okay, on number 10. Just because we're used to the exponential being first, I am going to rewrite this. You do not have to. You'll get the same answer, but I just think it's easier to rewrite this so that my 9x is going to be, 9 to the x power is going to be on the left. Is less than or equal to 1/3. Because if you look at it, I just flipped it over. The point is pointing to the 9. The point still has to point to the 9. I just think it's easier to read that way. So now I have 9 raised to the x power, that's going to be my y1. And if you'll pay attention to the way that they've done their window, it definitely helps you to be able to see these. Exponentials, sometimes they go so fast, they go up so fast, that if you're in the standard window, you'll never be able to see them. So pay attention to the way that they've done their windows. It's definitely helpful. So they've gone from -3 to 3, counting by ones, and from -1 to 2, counting by ones. So, looks like that. Now, if you read the way we rewrote this, I am looking for where the exponential, the curved piece, 9 to the x power, is less than 1/3. So I'm looking for this piece that's less than. So that's, the intersection is at -0.5 or -0.5. It goes from -infinity to that point. And that -0.5 or that -1/2 is included because this says less than or equal to. Are they okay? Alright, you should be able to complete the 11 and 12 on the back. It's just kind of a combination of the different things we've done. They're not all inequalities, but some of it is.